Lines and planes in space are three. Number one, lines. Let's suppose that the point M0 on the line L and the vector V is parallel to the line L. So the point 0 is given, for example, here. And this is vector V. We know V and M0, and we want to find the equation of the line L. Let's suppose that the point M is any point on this line L. Now the vector M0M will be parallel to the vector V. So M0M parallel to the vector V. But the vector M0M will be given by x of the end minus x of the beginning, x naught minus x0 times I plus y minus y0 times j plus z minus z0 times k. So because of M0M is parallel to V, so it exists a real number t or lambda where M0M equal tv. But t times the vector v is ta plus times I plus ta times j plus ta times k. So now we have x minus x0 equals ta. So we can write x minus x0 equal ta, and y also y minus y0 equal tb and tc. So y minus y0 equal tb and z minus z0 equal t times c. So I can take x0 to the other side. So x equal x0 plus ta, y equals y0 plus tb, z equals t0 plus z0 plus tc. So these three equations here are the equations of the line L, where t any real number. If a is not 0, I can write x minus x0 over a equal t, if a is not 0. If b not 0, also I can do the same, if c not 0. So if I suppose that all of them are not 0, so the product is not 0, so I can write x minus x0 over a equals y minus y0 over b equals z minus z0 over c. Even without writing equal t, I can delete this part. Okay. Let's take an exercise. The vector AB is equal to xb minus xa, so it's 1, 2 minus 1, so it's 1i, plus yb minus ya, 1 minus minus 3, it's 4. J, 4 minus 5 minus k. So let's take, if we take the point A, 1 minus 3, 5 on the line AB, so we can write the equation of the line as x minus x of the point 1 over 1 equal over 4 equal over minus 1 equal t. Here y minus y of a, so it's y minus minus 3, z minus za 5. If we take the point b, so the solution is finished here, and we can solve using another method using the point b. It's 214 on the line AB. So we can write over 1 equal over 4 equal over minus 1. This is from the vector AB. This will not change. So x minus x of b is 2, y minus 1, z minus 4. To verify that the solution is the same, if we take the point A, for example, we can verify that this point exists here also in the second equation. Why? If I give x1, so give x1 here, and y minus 3, and z 5, you can verify that 1 minus 2 over 1 equal minus 1 equal minus 3 minus 1 over 4 minus 1, 5 minus 4 over minus 1 also. Also, if we put point B here, the point B, x2, y1, x2, y1, z4, so it will be correct. Because 2 minus 1 over 1 equal 1. And 1 plus 3 over 4, it's 1. 4 minus 5 over minus 1, 5 is. So we can choose one of these two equations as equation of the line L or AB. Planes in R3. If the point M0 is given on the plane B and the vector N is orthogonal to the plane B or perpendicular to the plane B, N is given, M0 is given. To find the equation of the plane, let's suppose that M0 is any point on the plane. So we can sketch here, and the point M is any point, M0 given, and N orthogonal to the plane. So the vector M0 M will be orthogonal to the vector N. So because it's orthogonal, so we can write M0 M times inner dot product or inner product N will be 0. M0 M is given by x minus x0 times I plus y minus y0 times j plus z minus 0 times k. So inner product N, I will take x of N times x of the vector here. So it will be given here plus y of N times y of the vector M0M plus z of N times z of M0M equal 0. This is the equation of the plane B. Exercise. Find an equation of the plane B passing through the point M0 and orthogonal to the vector N given here. So the formula that the vector 4 from the vector here and times x minus x of the point M0, 1, plus the number here, minus 12, times y minus 2, plus the number here, 11, times number 11 times z minus 3 equals 0. This is the equation of the plane E. Exercise. Find an equation of the plane ABC where A and B and C are given. The problem is how to find the equation of the normal line, the vector orthogonal to the plane. Remember that always the vector AB cross product AC will be orthogonal to each of AB and AC. So we will use this idea. Let's calculate the cross product AB-AC. What is the vector AB? The vector AB will be 1i minus 3j minus 3k. What is the vector AC? It's minus 2i plus j 2 minus 3 minus k. So let's calculate the cross product AB cross AC by writing the determinant is equal to determinant I, j, k. Then the vector AB is given by 1 minus 3 minus 3, 1 minus 3 minus 3. Second vector minus 2, 1 minus 1, minus 2, 1, minus 1. So let's calculate I times 3 minus 3, 3 plus 3, 6i. then j, I will take minus, there is a sign minus here, times minus 1 minus 6. So it's minus 7 times minus plus 7. Plus 7. Okay. K, I have 1 minus 6, so minus 5. So minus 5. Okay. So this is the vector n orthogonal to the plane A, B, C. And we can take any point as like the point A, for example, which is 1, 2, 3, exists on the plane ABC. Now let's write the equation of the plane. Will be 6 times x minus 1 plus 7 times y minus 2 plus z, the last number, minus 5 times z minus 3 equal 0. The next exercise, find the line L of intersection of the two planes B1, B2. So here we must find one point and vector parallel to the line. So to find the point existing on the line L, let's find any point exist on B1 and B2 together. So let's give, for example, Z0. So we'll have in the plane B1, on the plane B1, we have x plus y equal 3. And on the plane B2, x minus y equal 1. So by addition, you will have 2x equal 4. So x equal 2 and y equal 1. So we have this point x2, y1, z0 exists on B1 and on B2, exists on B1 intersection B2. This is first step. Second step, let's find a vector orthogonal. Let's find the vector n1. Let's suppose n1 is orthogonal to B1, the plane B1. So the vector n1 is the normal vector, will be given by 1, 1, minus 1, 1i plus 1j plus minus 1k. And the vector n2 orthogonal to the plane B2 will be the vector from here 1 minus 1, 1, 1 minus 1, 1. So now let's take the vector n1 cross product n2. So n1 cross product n2 will be parallel to the line L of intersection. What is L? L is the intersection line of these two planes. You can imagine that by sketching. If you didn't understand why this is correct, if you sketch, imagine sketch plane B1, sketch plane B2, sketch the vector n1 and n2. Then remember that this vector n1 cross n2 is orthogonal to n1 and orthogonal to n2 also. So the line L will be parallel to the vector n1 cross n2. Let's calculate the cross product of n1 and n2 by taking the determinant. Right, ijk as vectors. Then n1 is 1, 1, minus 1, n2, 1, minus 1. 1, then you will have 2, here I have 0i, then j, it will be minus 2j, then minus 2k. So this is parallel to the line L, and I have the point 2, 1, 0 exist on the line L. So finally the equation of the line L, let's write it in red. So it's x equal x0, 2 plus 0 times t, y equal 1 from here, plus minus 2 times t, minus 2t, z equal z0, 0, minus 2t. So these are the equations of the line L. Exercise, find an equation of the line L where A, 1, 2, 3 of the line and the line L orthogonal to the plane. So here the vector 1, 1, 1, 5, this is the normal vector of the plane. So this vector will be parallel to the line L. So the line L will be x minus 1, y minus 2, z minus 3 from the point 1 to 3 over. Now these numbers down comes from the vector n 1, 1, 5. The last exercise, find the intersection of the line L, x minus 1 over 2, y equal 1 minus 3 over 5 equals z plus 2 over 7, and the plane x plus 3 minus z equal to. To solve this exercise, let's write the equations of the line as x equal, if I write this equal to t, so x equal 1 plus 2t, and y equal 3 plus 5t, and z equal 7t plus 2, 7t plus minus 2, 7t minus 2. Then let's take the equation of the plane to equal x plus 3y minus z equal, let's repeat, instead of x 1 plus 2t, instead of y 3 plus 5t, instead of z minus 7t minus 2. Let's continue the calculation. So I have here 2t plus 2t plus 15t minus 7, so 17 minus 7, 10. Then I have here 1 plus 9, 10, 10 plus 2, 12. So we can write 10t equal minus 10, so t equal minus 1. So now let's go back to these equations, x, y, z. So x equal 1 minus 2 equal minus 1, y equal 3 minus 5 equal minus 2, z equal minus 7 minus 2 equal minus 9. So the intersection of the line L with the plane B is the point minus 1, minus 2, minus 9.